This lecture is on force distribution diagrams. What are those? Let's find out. So up to this point, we found internal forces at a section in a beam. So last time we took a section of a beam and we said, oh, at this point right here, what are the internal forces or what's the internal loading at that moment? Well, now we're going to try to find the distribution of loadings within the body and represent them as a function. And so we're going to want to know not only what's our internal resultant force here, but what about here and here and here. And we want to find a way to represent those loadings throughout the whole beam. And that's called a loading diagram. So here's an axial loaded member. And you can see that the load is distributed, right? So we've got part of the load applied at all different points here. And if we section it at a general point A, so we're going to try and keep things generalized here, we can define the N, that is the normal force, this guy, at any section. So when we draw this guy, this is our free body diagram, we've defined this as L minus X rather than some number, right? So that any place, if we sectioned it here, that distance would still be L minus X. And so we can write that sum of forces in the X direction as P, right? The P is in kilonewtons per meter, times L minus X, which is measurement in meters. And that's going to be equal to N. Okay, so in other words, this guy here is the applied force on our generalized diagram over here. And we can say that N is equal to that. And then we can write this as a function for N. So what's the force as a function of X? And as you can see, as X gets bigger, as I go out farther and farther here, my force is actually going to be smaller. And we get a nice linear distribution that we can see here of the forces as a function of X. In other words, at the section, if I took my section here, my internal resultant normal force would be here. If I took my section here, I'd have a much lower normal force. And that makes sense, right? As we get farther towards the end of this beam, we would expect that internal loading to be smaller. So that's a loading distribution diagram, okay, or in this case, a force distribution diagram. Now, more often, we're interested in shear and moment diagrams, and so those actually, if you look in the textbook, those take up a couple of sections of a chapter. And so let's talk a little bit about how we would create one of those. It's the same process that we just used to find that axial force diagram. So we'll start with just a quick description of beams. We've got three different kinds of common beams here, right? A cantilevered beam, a simply supported beam, which is supported at both ends, in this case by a pin and by a roller. And then we have an overhanging beam here, which in some ways is a combination of the two, right? This is essentially a simply supported beam, and then the overhanging part acts like a cantilevered beam. So we'll see those a lot in this course, right? Because they are the model that we use for so many of our different calculations. So let's take our nice example here. So here's a nice simple supported beam. And we're going to find a shear moment diagram, and it's going to give us a distribution of forces, of shear forces, Vx, and of internal moments, Mx, from 0 all the way to x. So that's our goal. So we have to solve a statics problem here, because we want to know what's going on in the whole beam, and that's a relatively straightforward one, right? We know, oh, okay. Let's see, 4 times 3, so I'd have a 12 kilonewton force. It's going to be at the center here, so then I'm going to have 2 support forces. So each of those is going to be half of that 12 kilonewton force, and that's where that 6 kilonewtons comes down here. So now we make our generalized section diagram, and that's what we have here, okay? So we're starting on the left side. I use my sign convention shear and moment here. The moment is bending upward. The shear turns my section in a clockwise direction. So I've got a support force, and then I have a downward loading that depends upon where my section is. In other words, where X is. And so take a look at this, and you might even pause this and make sure that you can understand what's going on here, why this makes sense. Why is my loading always going to be 3x? And we talked a little bit about sign convention. I always put my fixed part almost always on the left, and that makes it a little easier to remember that my shear goes down and my moment goes up in that situation. Okay, now we can write our second law equation in the y direction. So we're going to start with shear. We're going to find our shear diagram. And that shear diagram is always going to be in the y direction on a beam like this. And so I just look at my diagram, right? I've got 6k going up. I've got 3x going down. Again, that depends on where I've taken my section. And then I have v pointed down as well. And so there's my second law equation, and I can solve that. And here in this case I have a nice linear equation as well. I don't know why I always think linear equations are nice. I always call them nice. Nice linear equation. So we can see we start at, if we're right next to the beam, our shear is high, right? Because it's right here, and that the only force, this force is going to become very small as x becomes very small, and so V is going to equal to 6 kilonewtons. So at that point, at the middle, we don't have any shear at all. And then by the time we get over here, at the other end, the exact opposite is happening, right? This guy becomes really large, almost twice as much as this, and so V here has to be negative. The shear is high near supports. That's generally true. Because essentially, if we think about it, if I think about this, right, this part of my beam here, this support is, taking on a 6 kilonewton load. That load has to be passed on to the next section here, and that's what shear is doing. Okay, so this section is being held up by 6 kilonewtons. That section there is holding the one right next to it up with that same amount of force. And we see shear is 0 at the midpoint. And so that's an important thing to recognize too. We're looking for maximums, and we're looking for places where our value is 0. Now we do the same thing for our moment. Okay, so here's our moment equation around the axis of rotation at our section point. So we're using the same little generalized section diagram. And here we have a moment around this axis. If we choose this axis, we get rid of V. That's what we want to do, because we don't want to deal with V here, because that's going to vary, right? We have a function for that, but that makes things messy. So we're going to put our axis there. Then we only have two active loadings that create a moment, right? Our downward loading, our support load, and then we have a moment M, and that's what is acting on that section point, what the internal resultant moment is. So we end up with this equation over here, and we can straighten that out to give us an equation for M. And here we have a nice quadratic equation. Not as nice as the linear equation, but we'll call it nice. And we can map out that equation there. So this is a quadratic curve. It reaches its peak at the center. Okay, so the moment is telling us how much is this beam bending, right? So the radius of curvature of the beam is highest right here. And then it's 0 at here and here. Now why is it 0? Well, because this is a pinned, right? and this is a roller, and neither of those can support a moment. If there was a moment there, then the beam would actually move. And so it's got the equilibrium point is where there is no moment at that pin.